Okay, so I give up. This video was going to be about hexadecimal and octal, what they're all used for, and comparisons to why we'd use different ones. But uh, I have had interruptions, corruptions, the wrong renders. I think apart from a meteor falling from the sky or the house blowing it or something, pretty much every distraction. Okay, so I'm not actually going to be doing Octal because I'm just no. All right, so here we have what we previously learned here. The base 2 system versus the base 10 system. All right, so in this lesson, we're going to be going over hexadecimal uh, and what it is, used for, why we use it, basically. All right, so, as you can see in the base 10 system, 10 possible values here. A base 16 system we have here, it has 16 possible values. We can go up to 15 here. 0 counts as a value, so 16 possible values. All right. But you see here, this here is exactly the same as this as far as digits, and that works fine. We don't need to change that at all. But once we reach 10 here, I mean, we can't use two digits to represent 10, and the reason for this being, for instance, let's see, let's get my hexadecimal value here that I'm using because I've been using it every time. Might as well use it again. All right, so this is our hexadecimal value. And you may have seen one of these, for instance, in a BSOD, in a blue screen of death. When Windows OS crashes, there's like a blue screen. It's got technical data and, it's got error codes and memory locations, that sort of thing. You might have seen one of these, 0x with, something appended on the end here. All right, this 0x indicates that this value here is hexadecimal. All right. Now, going back to what I was previously talking about here, uh, the F here is equal to 15 and the A here is equal to 10. All right. Well, let's say that these were expressed in base 10, format using two digits here. So instead of writing, this letter here, let's assume it was going to use two digits here. All right. So let's see. It's 15 and 10. All right, there you go. 15 and 10. All right. Look at that and you say, okay, that's 15, that's 10. All cool. All right. Let's see. Let's look at another example here then. Let's say it was, let's use 0 and A. All right. So 0 and A, that would be 0 and 10. All right. So there we go. 0 and 10, obviously, right? 0, 10. But what if this was 0, 1, 0? Okay. And let's go up here. Let's say this was 1, 5, 1, 0. Huh. And you see also we are actually using hexadecimal here, so we can have up to 15. Um, but what if we were 1, 5, 10? You really can't tell, where it ends and where it stops in, certain areas. It just gets really, really confusing. So that is the reason that we have added these, other characters that are not digits, so we don't get confused. And we've used alphabet. All right, so A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. All right. So that's all well and good here, but how does this all fit together? I mean, we know that F is 15, we know that A is 10, but what do we use that for exactly? Well, uh, the binary form of hexadecimal, we need a certain amount of bits in order to, get the equivalent amount of, hexadecimal values. We have 16, 16 maximum values here for one of these hexadecimal characters, all right? That means whatever binary we use has to be able to hold equivalent or higher amount of values. I mean, for instance, if we have one bit here that has two values, 0 and 1, obviously we can't fit 16 values into 2. All right, so we add another bit here, one's place, two's place. That means we have 4 possible values because we count the 0. So this is 2 plus 1, 3, and plus the 0 is 4 possible values, right? Okay, so we add another bit here, the ones place, the twos place, and the fours place. All right, so 4 plus 2 is 6, plus 1 is 7, and we count the 0, so this is 8 possible, 8 possible values here. Well, 8 possible values is all well and good, but we can't fit 16 values in it, so we got to add another bit here. All right, so here we have the ones place, the twos place, the fours, the fours place, and the eights place. I don't know where I was going. Right place. Just tried to stop myself. Okay. So here we have 8 plus 4, which is 12, plus 2, which is 14, plus 1, which is 15. So we have a maximum of 15 here, but we add the 0 as a value, so we have 16 possible values. So that means that 4 bits, or nibble, can hold one hexadecimal character. All right, so this here is the same as this here. All right, so moving right along, A is 10, so we got to write the hexadecimal format of 10. So that would be 1010. So yeah, so this is the eights place and this is the twos place. So 8 plus 2 is 10. All right, so we have 15 here and 10 here. All right, so the way this actually works, though, is you don't just read this as 15 and 10. What you actually do is these are connected together. All right, so here we have two doubles here, these two characters here that are put together. All right, now for instance, if this was just 0xFA, that would mean that this here is the ones place, the twos place, the fours place, the eights place, the 16s place, the 32 place, the 64, and the 128. All right, so you see here that we've increased the size of our number. Before we had 15 and 10 here. I mean, if we had FF, that would be 15 and 15. We could actually, either way you write it, you can have the same amount of possible values, but one is easier to understand than the other. So, here you see that, this would be equivalency to this. Okay, so moving right along here, if we write the rest of this out, you see here we have a 1, 5. All right, so 1 would be 0, 0, 0, 1, and 5 would be 0, 1, 0, 1. And moving on, doing the rest of these, I'm not going to do that because I have it here somewhere. Here it is. All right. This whole thing here is equivalency to this here. All right. So you remember that each of these is equal to 1 nibble, right? All right. So got 1 nibble here, 1 nibble here, right? All right. So how many nibbles is equal to a byte? Well, if you recall from the previous, we have 2 nibbles equals 1 byte, all right? Or, you could also say that it equals 8 bits. So, you could say either 8-bit or you can say a byte. All right, so we're going to say we have a byte here, all right? So we have a byte here, 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 right? Because each of these represents a nibble. All right, so we have in total 4 bytes here. All right, now how many bits would we have then? We would have, well, how many bits is in a byte? We have 8. So how many bytes? We have 4. So 8 times 4 is 32. That means in total here we have 32 bits. And that is where the term 32-bit operating system comes from. Because the computer components, the registers and stuff, we won't be going over that here, but the registers and stuff, they will be using 32-bit registers. And obviously that's for another time. But yeah. So yeah, you see here, this is 32 bits, and this is most commonly, a value variable type that is used in programs. You've seen, like int and stuff. Int, in most cases, is referring to a int 32, which is this right here. All right, so this right here and this right here are the same value. All right. So uh, we have gone over the value and stuff. Let's see, we've gone over the prefix. 0x means that it's a hexadecimal value. Now we'll go over a little bit about why we need the prefix. All right, so the prefix here. Let's see, if I write this and I write this, all right, one of these values here is binary. All right, and the other is hexadecimal. Can you tell me which one is which? All right, well, obviously, this was hexadecimal and this was binary, right? Well, obviously, no. All right, so you can see here that they can, both look exactly the same, and that's why we use this 0x to indicate, okay, this is actually in hexadecimal value format here. And it's like if you wrote this out here, let's see, if this is bits here, then obviously, this is just the same thing, in bits, but this is a completely different value because this would be 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. All right, so you see this would be the hexadecimal bit equivalent. You see that these are two very different values. So that's why we use the prefix 0x. And depending on what languages you're using, sometimes you will have a prefix of a B to indicate this is a binary form. Here, sometimes programs have also, instead of a 0x, sometimes they'll have like an H to indicate that it is actually in hexadecimal. All right, it doesn't matter what they use, as long as they use something that makes it not, undistinguishable what it is. All right, so as you can see, that 0x shows us that. All right, so now I'm going to be going over why we need hexadecimal. All right, so in more intermediate and advanced things, you're going to be using hexadecimal in memory values, like pointers and stuff, or other values that are only distinguishable in hexadecimals. I mean that's what they're registered as in byte formats and stuff, and it can get really complicated due to conversions and stuff. I mean, you can do the conversions obviously because they're all attached, but it can get really confusing here. And I got rid of it, didn't I? I did get rid of it. Why would I get rid of that? Yeah, I'll copy it over again. All right, so this here was the binary equivalent to this hexadecimal value, right? And vice versa. All right. So if we were doing a a program and we needed a specific memory value, would it be typer for me to type 0xFA15DEBC, for our hexadecimal, or would it be faster for me to type 11110100101110111011101110. You can see one of them was much faster to type than the other. Uh, and both of these, again, are the same exact value. Now, how is that possible? How does one use up more space than the other and one's, like less? Well, since this is using more possible values for each character, that means that, we can have, more, values here instead of just having, for instance, the base 2 system here. We just have these two to work with. That means that once these two are up, we have to extend, right? Now, the base 10 system here, this has, a lot, more characters to work with, so this is going to be a lot shorter, right? Well, this has even more characters to work with here, so it's even shorter than the base 10 system here. All right, so you see that this shortened form here is actually much easier to copy over if you have to type it than this was. Both equal the same because we know F is equal to this. So that means instead of typing 1111, we can just type F, right? All right, so that is one of the main reasons we need hexadecimal, because things can get much more complicated in programming. And for instance, if we open a hexadecimal editor, uh, you can see the bytes in hexadecimal format. So remember, each of these is equal to a nibble. 2 nibbles is equal to a byte. That means 2 of these hexadecimal characters is equal to 1 byte. So this means this is a byte and this is a byte if we were looking at a hexadecimal editor. All right, so you'd have that to look at compared to if we didn't have a hexadecimal editor and we were just looking at the binary. All right, so what would that be? That would be 1111, 1111. Did I get the last one? Yes, I did. And then that would be, what was that? That was 1010 and then 1010. All right, so instead of just looking at this and saying, okay, that's FF and then AA, you'd be looking at this and just say, okay, let's see, that's 8 bits there. All right, so this is 1 here, and then this is 1 here. So this is in total 2 bytes here. All right, you can do that, or you can just say, okay, this is a byte and this is a byte, so we got 2 bytes here. You can see one is much faster than the other. And in programming, depending on what you're doing, can take long enough time as it is. So we want all the shortcuts we can. All right, so I was going to go over octal in this video and do comparisons on why we would use hexadecimal or octal depending on what what we're doing, what scenario we're in, and different optimizations about why we would use one, because we don't need the extra bit space and stuff for streams. But I'm actually not going to be doing that because I have literally done this video 16, 17 times already, and I've either had corruptions or interruptions. I had the computer crash one time. Oh, not the computer. Actually, the power. The power crashed, and it just gone. So out of all the things that have happened, the incorrect renders and I already said the corruptions and stuff, interruptions, people talking, people spamming me on Steam, all this other stuff. Yeah. So this is where I'm gonna end this here. But yeah, I hope this has given you a little bit more understanding of hexadecimal and what it is used for. How it makes it easier for a programmer to understand things better in shorter amount of times. and I hope it has, helped you understand how to convert hexadecimal to binary form and vice versa. Just like the previous video, this is stuff that I actually learned, myself as shortcuts. I didn't actually learn this from anyone. So, yeah, this is straight from the source, basically. Like, I didn't invent hexadecimal. I'm not saying that, obviously. Although when I was a kid, I did actually invent a base 18 number system without actually even realizing it. I was just doing, notes and stuff. And looking back at it, I realized that was actually a base 18 number system that I had made. Uh, kind of, kind of random for like a 6-year-old to do that. But yeah. Anyway, getting really sidetracked here. But yeah, basically, simple hexadecimal stuff that we've gone over here. We haven't gone over anything advanced, and probably won't be going over anything advanced for at least a while. But yeah, I think we're done here. I'm gonna stop this video, and for the love of God, please, please don't corrupt. All right, here we go.